The remainder of chapter 14 is about other types of molecules that have atoms in the oxygen group, that is either oxygen or sulfur, in single bonds to carbons. We've already talked a little bit about ethers since we know that they're the product of dehydrations for primary alcohols. That's certainly not the only way that ethers are made, but it's the only way that we'll talk about in this class. Ethers have carbons on both sides of an oxygen, versus alcohols that have the carbons on one side of the oxygen and a hydrogen on the other side. As a reminder, we'll often use our labels to indicate any sort of chain of carbons, in ethers and alcohols and lots of other places. Because ethers have carbons on both sides, and they don't have the OH bond, they're not able to intermolecularly hydrogen bond. Remember, that's between molecules rather than within a molecule. And will have very different chemical and physical properties than we'd see for alcohols. In IUPAC, ethers are named exclusively as side chains. They're never part of the main chain name, even if the only other functional group is an alkane. So when we're trying to name the molecules, we'll definitely not name it as an ether. Ethers separate the molecule into two carbon chains. The ether oxygen is never part of that chain, and so we'll have to choose from one side of the ether to name as the main chain, and the rest of the molecule will be a side chain named as a specific type of ether side chain. Most of the rest of naming the ethers is pretty standard. Once we have a main chain, we'll need to indicate the ether as a side chain. The ether side chains will always have two parts to the name in the form alk-oxy. The alk part will be the length prefix, like meth, eth, or prop, and that will indicate the number of carbons on the other side of the oxygen from the main chain. The oxy part just indicates the oxygen. So a 2-carbon ether side chain would be ethoxy, and a 3-carbon ether side chain would be propoxy. Let's work through naming an example ether. The first step to naming the molecule is to find the longest chain of carbons connected to the most important functional group. Since ethers are always side chains, we look first to see if there's anything else that's important on the molecule. On either side of the ether, we have only carbon-carbon single bonds, so we know this needs to be named as an alkane. The longer alkane will be the more important one, so we'll take our main chain from the longer right-hand side. The main chain name then is propane, based again on the right-hand side, because there are 3 carbons. Remember, the oxygen is never included in our count for the main chain, only the carbons. Connected to the first carbon of the propane is an oxygen, which we describe with a side chain name of oxy. Connected to that oxygen is a 2-carbon chain, which we describe with eth. Notice that the eth and oxy together are describing the side chain, rather than an ethyl describing an oxy that describes the main chain. So we use the length prefix eth, but we don't use il as part of that name. Anyway, the full side chain name for this ether is ethoxy, and it is attached on the first carbon of that propane, which means that we need to give it a number 1. Notice that we could actually move that ethoxy over 1 carbon to the 2 position of propane, and we'd have a different molecule, 2-ethoxypropane. So the 1 label is actually really important for this. Now try to name the molecule that's on the top right. See if you can identify the name of the molecule. The main chain should be larger, the larger cyclohexane, and the side chain should be methoxy for a methoxycyclohexane. Because the ether is the only thing on the ring, we don't need any sort of number. Now try the bottom left. The main chain is a propane. It has 2 side chains, a methoxy, the ether, and methyl. And as usual, they're listed alphabetically. So we'd have 2-methoxy, 2-methyl propane. Now try the last one. The final name should be ethoxyethane. Either side could be the main chain, and the other side would then be ethoxy. Since both positions are identical on the ethane before we add the ethoxy, there's no need for a number in this case. Ethers are actually quite a bit easier to name in common form than we just saw in IUPAC form. We just list each side of the ether as a side chain, and then we add the word ether. If 2 side chains are the same, we use the prefix di. So for example, the molecule in the top left has 2 methyl side chains, and we'd say dimethyl ether. Like common names for alcohols, the side chains are actually separate words. The ether on the top right has two different side chains, and so we'd list the side chains alphabetically, again as separate words. We'd have a benzyl, phenyl, ether. As a reminder, since people often get these confused, the benzyl is the aromatic side chain with an extra carbon, which we see on the right side. The phenyl is the aromatic side chain that is just the 6-carbon aromatic ring itself attached directly to something else, which here is shown on the left side. Now see if you can name the remaining molecules. In the next row, we have ethyl propyl ether. The ethyl side's on the left and the propyl's on the right. And then cyclohexyl methyl ether. The following row has tert-butyl methyl ether. The tert-butyl is alphabetized based on the butyl rather than the tert, which is the same as you would see for sec-butyl. Finally, we have diethyl ether. Now that we've talked about both alcohols and ethers, it's worth noting that alcohols and ethers are both considered saturated, and so they have an index of hydrogen deficiency of 0. We don't have to worry about the oxygen as part of that calculation, since it doesn't affect the ratio of carbons to hydrogens. So if, for example, we have C2H6O for a formula, we have the same index of hydrogen deficiency as we'd have for just the C2H6. This, in this case, is in the form of twice as many hydrogens as carbons plus 2 extra, C2H2 times 2 plus 2. So we'd have an index of hydrogen deficiency of 0, and therefore no double bonds or rings. With 2 carbons only, there's only one alcohol we can make, but we can also readily make an ether with the same formula. Whenever we have a formula that works for alcohols, there will also likely be an ether isomer, or more. If we do have unsaturation, like we see in the second formula, we can now incorporate double bonds or rings and still have lots of different functional groups available. The double bond can be between carbons, like we saw before, but it could also be between a carbon and an oxygen, and that would also be an isomer for the same formula. We can also incorporate the oxygen directly into rings at this point for an ether ring. Like always, we can tell a lot about the physical behavior of ethers just by looking at the types of intermolecular forces that are present. What force do you think is most important in a small ether like dimethyl ether? While ethers can't hydrogen bond with themselves, they still do have a dipole. Dipoles are significantly weaker than intermolecular hydrogen bonding like we'd see in alcohols or in water, but they're still significantly stronger than London forces that we see in alkanes. This graph shows the boiling points of normal, again that means straight chain alkanes, normal 1 alcohols, and then also ethers. The even carboned ethers are the symmetrical ethers, like dimethyl ether and diethyl ether, and the odd number ethers differ by just 1 carbon on each side, like ethyl methyl ether for 3 carbons or ethyl propyl ether for 5 carbons. As we look at the graph, you can clearly see that the dipole that's in the ethers, the yellow one, is stronger than the London forces of the alkanes, which are shown in blue, because they have a higher boiling point in every case for the same number of carbons. But they're still significantly weaker than the hydrogen bonding that we get from alcohols, which we can see as the red line. As we get more and more carbons, the difference between these groups becomes less and less important because most of the molecule ends up being the carbon part anyway. This graph shows the solubility of ethers as light blue points against our broken bar graph from the last section that showed the solubility of alcohols. Data is not nearly as reliable or readily available from the asymmetrical ethers, which is why some of the odd number data points are missing. But we can still clearly see a trend. Remember that the broken graph represents a huge scale difference for the first 3 alcohols compared with everything else. Ethanol is infinitely soluble compared with its ether isomer, dimethyl ether, which only has a solubility of about 71 grams per liter. You can see that comparison in the second column. We see limited solubility for the very small ethers, Nothing compared to the very high solubility for the very small alcohols. This makes sense because ethers can still accept hydrogen bonding from water, as shown by the dotted line between the ether and the H2O, but it can't contribute any hydrogens for intermolecular hydrogen bonding themselves. Like alcohols, this very quickly drops off to the point where we no longer consider even diethyl ether, which has 4 carbons, particularly soluble in water. In most cases, ethers don't readily react, which means they're great solvents for reactions. They can dissolve organic reactants without changing them. Diethyl ether is a really common solvent, so common that it's often just called ether in the same way that ethanol is sometimes just called alcohol. Another common ether solvent is tetrahydrofuran, or THF. You don't need to know that name or structure, it's just an example of a solvent that's an ether. If you do want to nerd out on connections, THF is related to another ether, furan. We don't do much with furan, a suspected carcinogen, although it is probably present in your coffee, although much below the level where it's toxic. But furan is closely related to a form of carbohydrates that we'll see later called furanoses. Similarly, puran, a 6-membered cyclic ether, is closely related to pyranose carbohydrates. Anyway, ethers are often solvents. This can sometimes make our life a little bit interesting because we often heat up solvents to facilitate a reaction, and ethers are ridiculously inflammable. Again, inflammable is the grammatically correct way to say something can light on fire or combust easily. This is aided by the high vapor pressures, meaning that there's a lot of vapor in the gas phase even at low temperature. Ethers can also react slowly with air to form peroxides, which have an oxygen-oxygen single bond. These peroxides are really explosive, so if you heat up an ether solvent too much, it might start on fire. I've definitely seen that happen. And if you let it all evaporate and keep heating it up, it might actually explode. I thankfully have not seen that happen. But other than the fire thing and the explosion thing, these really are great solvents. We spend much of our time talking about alcohols and ethers in this chapter, but because sulfur is in the same group as oxygen, we can make very similar functional groups by swapping out sulfur for oxygen. We call these analogous functional groups because they behave very similarly. We won't go into detail naming these or talking about reactions, but I do expect you to be able to identify the sulfur version of an alcohol as a thiol and the sulfur version of an ether as a thioether. In each case, we include the word thio, which comes from the Greek for sulfur. While sulfur is very similar to oxygen in most ways, sulfur is in the 3rd row of the periodic table, and it doesn't need to follow the octet rule anymore. It's much more flexible in its bonding, and it can be readily oxidized and reduced. A particularly important example of this is in our bodies, as the small peptide glutathione. A peptide is essentially a very short protein, and glutathione is a very short protein, or a peptide, that is the major active antioxidant in our bodies. The thiol of glutathione, highlighted in yellow, can be oxidized to a disulfide, a sulfur-sulfur bond that's quite stable. When it's oxidized, it reduces other things. So oxidation of glutathione helps protect our bodies from oxidative stress. The same type of thing that vitamin C does. Once glutathione is oxidized, it can be reduced back to its thiol form and reused or recycled, making it not only one of the most important antioxidants in the bodies, but also a perfect biochemical example of sustainability, since it can be reduced, reused, and recycled.